So, today we shall see this system of linear equations. System of linear equations. This is also an important concept in linear algebra. Here we shall discuss about consistency of a system of linear equations, and also we shall discuss how to find solution of this. A system of m linear equations in n variables can be written as a11 x1 plus a12 x2 plus a1n xn is equal to b1, a21 x1 plus a22 x2 plus a2n xn is equal to b2. Like this, m equations, am1 x1 plus am2 x2 plus amn xn is equal to bm. Here the coefficients where this aij, they belong to a field I for 1 to m, j from 1 to n, b I also belongs to this field, and x1, x2 to xn are variables or unknown that we have to find out, or in other words, solving the system of linear equations means we have to find unknowns x1, x2 to xn, so that these equations will be true. Here we are considering these coefficients aij are from a field f, and also the elements b1, b2 to bm are also elements of this field f. Here in fact we say that this system of linear equations is a system over this field f. In place of this field f, one can also consider the real field or complex field also. So, this system of m linear equations in n variables can also be written as this system can be represented as Ax is equal to b, where A is this matrix that A11, A12, A1n, A21, A22, A2n, AM1, AM2, AMN, and this X is, so this A is m by n matrix and X is this column vector, this matrix x1, x2 to xn. This is of size n by 1, and B is also a column vector or this matrix b1 up to bm. This is M by 1 matrix. So, this matrix A is called the coefficient matrix of the system. A is called the coefficient matrix of the system. Further, if B I is equal to 0 for all I, then the system is called homogeneous, otherwise it is non-homogeneous. Otherwise it is not homogeneous. So, here we shall discuss about consistency of this system, that means when solution exists for this system, and also we shall see how to find solutions. So, the following theorem gives the condition for consistency of the system as well as existence of number of solutions of the system. So, let A x equal to B be a system of linear equations, be a system of linear equations in n variables. Then we have the following results. The system is consistent if rank of the coefficient matrix A is equal to rank of the augmented matrix A tilde, where A tilde is this augmented matrix A B. Second condition says that if rank of A is equal to rank of A tilde, that means the system is consistent, and if this rank is equal to n, then the system has a unique solution. So, third result here is that if rank of A is equal to rank of A tilde and this is equal to k, and that is strictly n less than n, that is number of variables strictly less than the number of variables, then the system has infinite number of solutions, So, we are not proving this theorem, but we will use it and solve problems. One immediate corollary is that, so in case of a homogeneous system of equations, we get that the rank of the coefficient matrix is equal to rank of the augmented matrix, because all B I are equal to 0, Therefore, a homogeneous system Ax equal to 0 is always consistent, or always a solution exists for the system. Notice that for Ax equal to 0, this 0 0 0, that means all xi's are 0, is always a solution. So, we will have in fact the following lemma that tells that the collection of all solutions of a homogeneous system forms a subspace. Let S be the set of all solutions of this homogeneous system Ax equal to 0, then S is a subspace of this vector space Fn. This is not difficult to prove. We can take any two solutions in S. Let x y belongs to S, that means x and y be two solutions of the system Ax equal to 0 and alpha beta be any two scalars or elements of this field F. Then we shall see whether this alpha x plus beta y is a solution for the system or not. So, this can be written as alpha Ax plus beta Ay, and this is equal to 0. Since Ax equal to 0 and Ay equal to 0, we get this combination is also 0. This implies that alpha x plus beta y belongs to S. Hence, S is a subspace of this Fn, and therefore, this set of all solutions of this system Ax equal to 0 is called the solution space of this homogeneous system. So, we have the following definition: the set S of all solutions of Ax equal to 0, this homogeneous system is called the solution space of this system, is called the solution space of this system. So, next we shall see some examples of system of linear equations, and we shall apply the results in theorem 1 and check whether that system is consistent, and if this system is consistent, then we shall find all solutions of that system. So, we have following examples. So, here we will ask that find all solutions all solutions of the following systems if consistent. So, first system is this: x plus 2y minus 3z is equal to minus 1, 3x minus y plus twice z is equal to 7, 5x plus 3y minus 4z is equal to 2. So, we shall see whether the system is consistent first. Here the coefficient matrix is A is this matrix, that is 1, 2, minus 3, 3, minus 1, 2, 5, 3, minus 4. Augmented matrix is A tilde is the matrix 1, 2, minus 3, minus 1, 3, minus 1, 2, 7, 5, 3, minus 4, 2. So, next we shall find out rank of these two matrices and check whether they are equal or not. So, for this we consider the augmented matrix only. So, now we consider the augmented matrix and find its echelon form. So, the matrix is 1, 2, minus 3, minus 1, 3, minus 1, 2, 7, 5, 3, minus 4, 2. So, for finding this echelon form, here we replace this row 2 by row 2 minus 3 row 1, and also this row 3 we replace by row 3 minus 5 times row 1. So, the matrix we get is like this: 1, 2, minus 3, minus 1, 0, minus 7, 11, 10, 0, minus 7, 11, 7. So, next again we apply elementary row operations, and here we replace this row 3 by row 3 minus row 2. So, the resultant matrix will be 1, 2, minus 3, minus 1, 0, minus 7, 11, 10, 0, 0, 0, minus 3. So, here in this echelon form of the augmented matrix, we can see that first 3 columns of this matrix is the echelon form of matrix A. So, therefore, the rank of here first 3 columns is the echelon form of the coefficient matrix A of the matrix A. So, here in this echelon form of A, we are getting a 0 row. So, rank of this coefficient matrix is 2 and rank of this augmented matrix A tilde is equal to 3. So, therefore, rank of A is not equal to rank of this augmented matrix A tilde, and hence the system is inconsistent. The system is inconsistent. That means the system has no solution. The system has no solution. So, next we will see another example, that example 2. Here the system is like this: 2x plus y minus twice z is equal to 10, 3x plus 2y plus 2z is equal to 1, 5x plus 4y plus 3z is equal to 4. So, here again we will find rank of the coefficient matrix and rank of the augmented matrix for checking the consistency condition. So, therefore, we find echelon form of the augmented matrix. So, here we find echelon form of the augmented matrix, which is given by 2 1 minus 2 10 3 2 2 1 5 4 3 4. So, here we make the following operation, that elementary row operations, that row 2 we replace by twice row 2 minus 3 row 1, 3 times row 1, and R3 we replace by twice R3 minus 5 times row 1, and we get the matrix B like this, that is 2 1 minus 2 10 0 1 10 minus 28 0 3 16 minus 42. So, next we apply the following elementary row operation, that is row 3 we replace by row 3 minus 3 times row 2 and get the matrix be like this, that is 2 1 minus 2 10 0 1 10 minus 28 0 0 minus 14 42. So, in the echelon form of the augmented matrix, the first 3 columns is the echelon form of the coefficient matrix. So, notice that rank of this coefficient matrix is equal to 3 as well as the rank of the augmented matrix, both are equal to 3, and that is equal to the number of, this is equal to the number of variables, and hence the system is consistent. Hence this system is consistent. So, here we shall see how to find solution of this system. So, from this echelon form of the augmented matrix, we get following system, that is the echelon form of the given system. So, echelon form of the augmented matrix gives the system twice x plus y minus twice z is equal to 10, y plus 10z is equal to minus 28 and minus 14z is equal to 42. So, from the last equation, from third equation, we get z equal to minus 3. Putting this in equation 2, we get y is equal to 2, and finally from equation 1 we get x equal to 1. So, therefore, the unique solution of the system is x equal to 1, y equal to 2 and z equal to minus 3. So, next we will see another equation, system of equations, and this third system is like this: x plus twice y minus 3z equal to 6, twice x minus y plus 4z is equal to 2, and 4x plus 3y minus twice z is equal to 14. So, for this system also we find echelon form of the augmented matrix, and here the augmented matrix is like this. So, here we find echelon form of the augmented matrix. So, the augmented matrix is 1, 2, minus 3, 6, 2, minus 1, 4, 2, 4, 3, minus 2, 14. So, we apply this elementary row operations that we replace row 2 by row 2 minus twice row 1 and row 3 we replace by row 3 minus 4 times row 1 and we get the matrix be like this 1 2 minus 3 6 0 minus 5 10 minus 10 0 minus 5 10 minus 10. Then applying this elementary row operation that replacing row 3 by row 3 minus row 2 we get the matrix be 1 2 minus 3 6 0 minus 5 10 minus 10 and 0 0 0. So, here you see that the rank of the coefficient matrix A is same as rank of the augmented matrix and that is equal to 2, but that is strictly less than 3 the number of variables. Hence, the system is consistent and has infinite number of solutions. Infinite number of solutions. So, next we will find the solutions of this system. So, again from the echelon form of the augmented matrix we get the system be like this. So, here the echelon form of augmented matrix gives the system. So, this system is like this, that is twice x plus y minus twice z is equal to 10, y plus 10 z is equal to minus 28. Sorry, that we will get this. Sorry, we will not get this one. This system is like this: x plus twice y minus 3z equal to 6 minus 5y plus 10z is equal to minus 10. So, this system we get from the echelon form of the augmented matrix, or we can write this system be like this, or x plus twice y minus 3z equal to 6 and y minus twice z is equal to, that is 2. So, here we have 3 variables and 2 equations. So, one variable we take as free variable. We take this variable z as the free variable. In fact, the variable which do not occur at the beginning of any equation in the echelon form is called a free variable. So, z is a free variable here, free variable here. That means it can take any value of the field. So, let z is equal to alpha and alpha belongs to this real numbers. So, from equation 2 we get then this value of y is equal to 2 plus twice alpha and value of x will be 2 minus alpha. So, the set of all solutions, the set of all solutions of the system is like this: 2 minus alpha, 2 plus twice alpha, alpha, such that alpha belongs to the set of all real numbers. Here we are considering the system over this set of real numbers. That is why this alpha will vary over all the elements of this real field. So, next we will see another example, and that is a system, homogeneous system of linear equations. So, next example is a homogeneous system of linear equations. So, here find all possible solutions of the system below. Also find the dimension of the solution space. So, here the system is like this: x plus twice y minus z equal to 0, twice x plus 5y plus 2z is equal to 0, x plus 4y plus 7z is equal to 0, x plus 3y plus 3z equal to 0. So, this is a system of linear equations, and this system is a homogeneous system because all these bi's are equal to 0. So, here we shall find out rank of the coefficient matrix to check whether the system has unique solution or infinite number of solutions. So, echelon form of the coefficient matrix is matrix. So, the coefficient matrix is given by 1, 2, minus 1, 2, 5, 2, 1, 4, 7, 1, 3, 3. So, here we apply the following elementary row operations that Row 2 we replace by row 2 minus twice row 1. Row 3 we replace by row 3 minus row 1. Row 4 we replace by row 4 minus row 1, and we get this matrix here, that 1 2 minus 1 0 1 4 0 2 4 0 2, and this will be 8, and 0 1 4. So, here we next apply the following elementary row operation, that we replace row 3 by half of row 3 and get the matrix be like this: 1 2 minus 1 0 1 4 0 1 4 0 1 4. So, here all these 3 rows, row 3, row 2, row 3 and row 4 are identical. So, here we replace this row 3 by row 3 minus row 2, and row 4 also we replace by row 4 minus row 2 and get the matrix be 1 2 minus 1 0 1 4 0 0 0 0 0 0. So, from here we get that rank of this coefficient matrix A is equal to 2, and this is strictly less than the number of variables, that is 3. So, the system has infinite number of solutions, infinite number of solutions, and these solutions we get like this. So, we get the system below from the echelon form of the coefficient matrix, that is also called echelon form of the system, and it is x plus twice y minus z equal to 0 and y plus 4z is equal to 0. So, again we consider this z as free variable, that is a variable which does not appear at the beginning of any of the equations in echelon form. So, z is the free variable. So, let z equal to alpha, that belongs to R, then we get y is equal to minus 4 alpha and x is equal to 9 alpha. So, this set of all solutions or the solution space, the solution space of the given system is this set S, that is consists of all vectors like this: 9 alpha minus 4 alpha alpha, where alpha belongs to the set of all real numbers. Next, we find out the dimension of the solution space. So, the dimension of the solution space S is also related with rank of the matrix A. Here, if we consider this matrix A as a linear transformation, then this S will be the nullity of this linear transformation A. Therefore, from rank nullity theorem also we get this result that if we think A as a linear transformation, then S is the null space of A. So, from the rank nullity theorem, we get that dimension of this solution space S is equal to total number of variables, that is 3, minus rank of A. So, that is 3 minus 2, that is equal to 1. So, this is how we solve system of linear equations, both homogeneous and non-homogeneous, and we shall come across this system of equations later on while finding eigenvalues and eigenvectors of matrices. So, next we shall discuss about this another important concept in linear algebra is this eigenvalue and eigenvector of matrices. This is an important concept of linear algebra, and this is very useful in engineering and sciences. Engineers and scientists, they come across this concept of eigenvalue and eigenvectors quite often. So, first we shall give definition of an eigenvalue. So, here basically we find eigenvalue and eigenvectors of square matrices. So, let A be an n by n matrix over a field F, then an element of F, an element lambda in F is called an eigenvalue of A if there exists a non-zero vector x in f n such that this equation holds A x is equal to lambda x. Here we consider this x as a column vector, that is, here we consider x as n cross 1 matrix or a column vector. So, if this lambda is an eigenvalue of A, if lambda is an eigenvalue of A and x is a non-zero vector such that a x equal to lambda x, then x is called an eigenvector corresponding to the eigenvalue lambda. Notice that eigenvectors corresponding to lambda need not be unique. There may be several eigenvectors corresponding to an eigenvalue. So, here in fact, if we have this following lemma that says that if x1 and x2 are eigenvalues, two eigenvectors corresponding to an eigenvalue, then their sum is also an eigenvector corresponding to the same eigenvalue, and also scalar multiple of any eigenvector will be again an eigenvector. So, in other words, if we include the 0 vector to the set of all eigenvectors corresponding to lambda, then that forms a subspace. So, here we consider that let A be an n by n matrix and lambda be an eigenvalue of A. Let S be the set of all eigenvectors corresponding to lambda. Then this S union the 0 vector is a subspace of this field f n. So, here this proof is not difficult, it is trivial. So, let us consider let x and y be two eigenvectors corresponding to lambda and alpha beta be two scalars from f. So, here this alpha x plus beta y will be an eigenvector corresponding to this eigenvalue lambda or not, that is what we will check. So, A of alpha x plus beta y is equal to alpha a x plus beta a y, and this is equal to alpha into lambda x plus beta into lambda y, or this can be written as lambda times alpha x plus beta y. So, this S union 0 is a subspace, and this subspace is called eigenspace corresponding to the eigenvalue. We give this definition of an eigenspace. So, if S is the set of all eigenvectors corresponding to an eigenvalue lambda of A, then the subspace S union 0 is called the eigenspace corresponding to this eigenvalue lambda. So, let us see an example quickly. Here we consider this matrix. Consider this matrix A be like this 5, 4, 1, 2 over this real numbers, of course, and a vector x be like this 4, 1. Now, this Ax, that is 5, 4, 1, 2, that is multiplied by 4, 1, that gives 24, 6, and that is 6 times 4, 1. So, that is equal to 6 times x. So, this implies that 6 is an eigenvalue of A, and 4, 1 is an eigenvector corresponding to the eigenvalue 6. So, we stop this lecture here, and in the next lecture we shall discuss about a method to find eigenvalues and eigenvectors of matrices. So, that is all for this lecture.